So I'm the only non-professorial speaker here, the non-academic speaker. So there won't be any graphs, there won't be any equations, it's just a perspective. Hopefully you'll get a sense of what Professor Venkat's contribution has been. I'm going to talk about a very different area than what you've heard so far. It's his contribution in the area of molecular design or materials design, something that has had a very seminal impact in this whole field. This is an area that has grown very rapidly in the last 10 years. Not a single day goes by when you don't hear a news article or a paper that says computers were used to discover a new molecule, a new drug, a new protein, even COVID vaccines, a new catalyst. The field has really exploded. These days, the names are somewhat different. People call it in silico design. People call it discovery informatics, material informatics, materials genome. But at the heart of it, it's really how do we use computers to discover new materials. What I want to show here in the next 15, 20 minutes is some of the foundational ideas in this area were laid back almost 30 years ago. Professor Venkat played a major role in that. Professor Stephanopoulos, who was here, had some groundbreaking work. The foundational ideas are still the same. But time has come now that we can now leverage those ideas to fast forward and accelerate materials discovery. So I want to start with the simple problem definition. What is the problem? The problem definition is very simple, that if I asked you a desired set of material performance targets, so given a set of desired material performance target, whether it's the physical or chemical properties, the cost of scaling of the material, the carbon footprint, which is quite important these days, the energy required, so some desired performance metrics, what is the best material or material formulation that will give you those properties? It's a very simple problem. The definition of materials design hasn't changed in almost a century. But I want to start with this first paper that Professor Venkat wrote back in 1994. That's almost 30 years ago, which for the first time showed that how you could use computers to discover these new materials. It was a radical idea at that time because new materials discovery was always an experimental sport. You always had this brilliant chemist who would go to the lab, hypothesize the material, test it. If it works, he has a discovery. If it doesn't work, he'll tweak it. And the cycle goes on and on and on. That's the Edisonian cycle of materials discovery. Not much has changed in many parts of materials discovery, but this was the first paper that claimed that you could programmatically search this through a computer. The idea was picked up by a number of newspapers. Professor Venkat, you might recall, Dallas Morning News covered this quite extensively back in '95. This is, again, 30 years ago. But that was the foundation. So what exactly was done in this area? So I see a few students here. When you get a chemical engineering problem, the first thing they teach you is deconstruct the problem, break the problem down into small pieces, and then solve the sub-problems, which eventually, when assembled together, will give you the full answer. That's exactly what we did here in molecular design as well. We broke it down into two sub-problems. The first one is what we call the forward problem, which is if I give you a structure, how do I predict the performance? So that's given molecular structure, predict performance. It's the reverse problem, the inverse problem that we are really interested in solving, that if you give me a performance target, then what is the molecular structure? But it turns out that you can't solve the inverse problem without solving the forward problem. So these problems are coupled. So hence, we have to solve both the sub-problems. The forward problem is really a predictive problem, and there are many ways to solve it. If you have the luxury of the first principles knowledge, build a first principle model to go from structure to property, which we have done in many cases. If you have the luxury of a lot of data, which is becoming true now, then you could build a data-driven model. But even better is hybrid models, which is a combination of first principles and data-driven, where you don't have as much fundamental understanding. And that is absolutely the case in many industrial examples that I'll show you in a few minutes. Once you have the forward problem solved, the reverse is the search problem, where you could use many different search methods to solve the problem. You could use deterministic optimization if the search space is continuous. You could use stochastic optimization if it's discontinuous, or you could use a combination of them. But this was the basic foundation that we wrote back in '99. The basic foundation of the basic construct hasn't changed in the last 20, 25 years. What has changed is the complexity of the forward models. What has changed is the complexity of the inverse problem models. The problem size has grown, but the basic construct has remained the same. I'll make the point even more emphatically with a number of examples that I'll show from various different arenas of material design, which are quite disparate at the face of it, but they all use the same underlying principles that you have to have a forward and inverse problem solved together. So let's look at that. To do this thing, I've broken down the whole evolution of the space or this field, at least from my perspective, in chunks of 10-year time frame. So I call the first 10 years from 85 to 95 as the early years of design. There were very few people, very few groups that were talking about this at that time. I've highlighted 3 papers. They're not the only papers, but 3 papers that I thought were fundamental in progressing the field forward. One was from Professor Stephanopoulos' group in 94-95 timeframe, where he first systematically showed that how to solve the inverse problem using a combination of mathematical optimization and some human interaction. That was the first structured way of coming back and solving the search problem. The 2 examples on the right is from Professor Venkat's group in 94, and then Professor Ghani's group in early 90s. They said, well, I can push the boundary even further. Why do we need even a human interaction? We can programmatically solve it in a computer if we can formulate or codify the forward knowledge properly. The algorithm that were used in Professor Venkat's group was stochastic-based, and the algorithm that were used in Professor Ghani's group was deterministic-based. And they both have their pros and cons. But these 3 papers, this trifecta of papers, to me, in my mind, laid the foundation that a proof of principle was established, that if you are able to codify the fundamental understanding, then you could systematically or programmatically search through an entire materials database to find the best materials that meet your desired properties. That was the first 10 years of design. Based on this success, we moved to the next 10 years, which is what I call the middle years. And I was a PhD student at this time with Professor Venkat working on some of these problems. What we did here was 2 extensions on the previous work. First, we migrated from academic problems to real-world industrial problems. And I'll give you a few examples of what we had done. Second, we recognized that the optimal molecule is not a molecule, but rather in an industrial setting, it's a mixture of molecules. It's a formulation. So the mixture gets more and more complicated. And third, we realized that it's not the material properties that matter. It's the material performance that matters. How does the material perform in a real-world industrial setting? So we had to model the performance portion of it, which again meant the fundamental first principles models at the back end of our models were going to get more complicated. You won't be able to read this thing in the back, but I want to give you 3 examples for real-world problems. First one was for Lubrizol. Lubrizol is a company that makes fuels additives. The problem they gave us was that they wanted to make an additive package that, when mixed with a gasoline mixture and introduced in your car, has a cleansing effect. So what's shown here is the intake valve of a car engine. And the metric of relevance here was that if the car ran for 1 million miles, the amount of deposit on your intake valve has to be less than a certain amount. So it's a very clear performance measure that you have to manage. The design problem was that what additive molecule or additive molecules will give you that performance. So we used the same idea of a forward and inverse model. In this case, the data was sparse, the data was noisy, so we couldn't build purely fundamental models. We had a kinetic model that showed how the additive will degrade in a thermal environment, and coupled that with some data-driven models to go from structure to property. And then finally, we covered the inverse problem through a search algorithm. And we were able to give some additive packages to Lubrizol that they experimentally proved that it worked and commercialized. The second example is from a completely different application. It's rubber formulations. This was a problem that came to us from Caterpillar. Caterpillar makes these huge earth-moving equipments. They have these huge rubber components, tires, rubber mounts, rubber hoses, and so on. These equipments are used in extremes of conditions. Whether you are talking about sub-Saharan desert or in extreme cold weather conditions, whenever one of the units fail, one of the equipments fail, there is downtime and there's capital loss as well. So what they wanted was a new rubber formulation that will withstand, that will show long-term durability, that will have a long-term mechanical performance over 10 to 15 years. Again, same kind of design problem. It's not one single molecule, it's a formulation. What kind of rubber, what kind of cross-link system, what kind of activator system, what kind of additive, does all that things go together in the formulation? We use the same approach, a forward and inverse model, I'll show you in a second, but we're able to deliver to them a couple of new rubber formulations that they could scale it up to meet the performance. The third example is again a different class of materials. This comes from catalysis. While we were making this progress in rubber and fuel additives, we also had a very active group in Purdue. This is circa early 2000 timeframe, when we had a very strong catalysis group. Professor Nick Telgas was leading that whole center for catalysis. Professor Lauterbach was there, who was doing high throughput experimentation, so we were getting more data coming in. And we had Professor Thompson, who was doing DFT calculation, which further enhanced our forward modeling predictions. The problem here was ExxonMobil was interested in converting propane to aromatics, and they were looking for a catalyst or catalyst system that will maximize the yield for aromatic conversion. Again, the same approach was used, that if I could understand at fundamental level how does the molecular structure of a catalyst lead to an enhancement in the property or the final aromatic production, then I could scan through the entire zeolite database and find out the best structure that will give you the highest aromatic content. That was what was done. The point I was trying to make with these three examples is these three examples show three different kinds of materials, completely disconnected from each other. But the underlying concept or the construct is still the same. In the first case, in fuel additives, look at the forward model. It was a combination of kinetic model, the portion that we understood that we could model from first principles modeling, and there was a portion that we didn't understand fully well, but we had the luxury of data. We bridged that with a data-driven model. This is called hybrid models today, but this was done almost 20 years ago. And the reverse was through stochastic search algorithms. In the case of rubber, we had a little bit more understanding of the fundamental physics. So our forward models was a population balance kinetic models inspired by Professor Ramakrishna's work. We had the kinetic parameters modeled through molecular dynamics, TFT, that was coming up at that time. And we had to predict the performance of these materials in an actual environmental setting where rheological properties were important, mechanical properties were important, and they eventually went into a part, so finite element design was important. So all of these different kind of fundamental models were merged together to go from structure to performance. The reverse was done by, again, stochastic algorithms. And the last example was on catalysis. The catalysis, again, a combination of first principles models, some high throughput experimentations, and DFT. But the trend you'll see is the complexity of forward models is increasing. And the reason that's increasing is over time, the computational power that we had was also increasing. So we could leverage that computing power to go in that direction. So what happened after this was, post-2005, 2006 timeframe, the number of publications in this area really exploded. This is a chart I made from Web of Science, doing a keyword search on either computer-aided molecular design, in silico design, or material informatics. And you see that there's clearly an exponential increase in publications post-2006. And in 2006 to 2014, that time frame, people were now screening large databases. It was not hundreds of molecules, but thousands of molecules that were screened programmatically. DFT was becoming more democratized, so we could do large-scale DFT calculations. And certainly, high-throughput experimentation was becoming the norm. So you had the luxury of doing a lot of experiments in parallel that helped in this forward modeling process. The last 5 years have been phenomenal, because the models are now just reactive. They are predictive. I could actually predict a material in advance, and then somebody can go and experimentally and test it. And we have so many publications that have shown that that concept works. The results have been experimentally validated, and there's an increasing amount of focus on energy transition. How do we find carbon capture materials? How do we find a better material for blue hydrogen and so on? And I'll show you 2 examples that ExxonMobil is working on. Okay. So what made this jump possible? So why did it take so long for computer-aided materials design to pick up? I think there are really 2 answers to it. First is the whole modeling construct was improving. Multi-scale modeling, I mean, a lot of people, our experts here, has really gone tenfold in the last 10 years. You could do now quantum mechanical calculations at thousands of atoms. You could do MD at billions of atoms. The computing power, the modeling capability has really gone up. And that's the chart on the left. In fact, the 2013 Nobel Prize Committee also recognized that computer is now an important tool for chemists, and they could actually compute through a lot of different ideas. At the same time, while the models were improving, the computing power was changing also. We were breaking Moore's law. Computing was increasing faster and faster. What I can compute on my iPhone today would take months to compute on a supercomputer almost 20, 30 years ago. So that power of computing really helped. And now I can write fundamental models at the electronic level and still be able to solve it very quickly. The latest trend is quantum computing, which only takes it even further. So this combination of enhanced molecular modeling plus enhanced computing power is what drove this exponential growth, and more to come actually in this area. So I want to take the last couple of minutes just to show this is not just a concept that stopped, but we are actually using it very actively in our own company to solve some of the biggest problems we have. I'm going to give you two examples. First is materials designed for CO2 capture. Carbon capture is by far the most important problem of our generation. What's shown here is the two big sources of carbon emitters, the industrial sector and the power sector. Between the two, almost 2/3 of the carbon emissions come from there. So there's an imperative to capture carbon from these sources. Now, carbon comes from different concentrations. If you are talking about industrial source, the range is anywhere from 10 to 12 to 40%, depending on if it's the back of an FCC or the back of a SMR. Or if it's a power source, it's 4 to 12%. The materials are different depending on what the carbon concentration is. And I'm not even talking here, there's a lot of big emphasis in Biden's organization on taking the carbon from the air, which is at 0.04%. But even if you just stick with point sources, the concentration varies quite a bit. Now, the industry has a solution, and that's called liquid amines. That works, but it has some scale-up issues. Cost is high, footprint is large, can't be applied everywhere. So we are looking for new kinds of materials that can solve this problem. A paper that we published in Science last year talked about a class of materials called MOF, metal organic frameworks, where if you at the molecular level tune the structure, you can significantly enhance the capacity for CO2 uptake. Now, that was done in a typical experimental fashion where you systematically altered the structure to look through it. But the issue is the world has almost 100,000 MOF structures theoretically identified. You can't systematically go through one by one, even if you had the whole army of brilliant scientists in your lab. So there has to be a better way to solve this whole problem, which is where we are using these ideas from computer-aided materials design. We are scanning through MOF databases to find the structures that are most relevant for carbon capture. We use molecular dynamics and high-throughput DFT, HT-DFT, to figure out relevant figures of merit. And figures of merit is just the first step. That scales down the molecule from hundreds of thousands of MOFs to maybe a few hundred MOFs. But then you have to couple that with the process side of things. How will the material perform when you subject it to a real flue gas stream, which has a certain condition, certain contamination? So we have to couple it with the process model. And that leads me to the final performance criteria, that out of the couple of hundred MOFs left now, maybe we can narrow it down to 50 such MOFs, which we will go in the lab and then theoretically then check it out. The inverse problem is once we have this thing, I can then fine-tune it. I can fine-tune for the process parameters. I can fine-tune it for the molecular parameters. Or I can even go through structures that people haven't discovered yet experimentally, but theoretically we can say these structures exist. So they are new materials that people haven't, that could be promising. So this is a very active area. The work is still ongoing. But I think the foundation that Professor Venkat laid 30 years ago still is quite relevant for this particular problem. The last one I have is very quickly on polyethylene design. Completely different problem. The world is growing. The population is growing. People need convenience. People need still plastics, even though plastics have an issue with recycling and so on, which we are solving in general. But there is still always a demand for new kinds of polymers. Polyethylene is our flagship polymer. And the development cycle for finding a new grade of polyethylene is almost 10 years, going from the catalyst discovery to making the product and launching it. So it's a 10-year cycle to make the product. So the question we have asked ourselves is, can we reduce the product development cycle life by more than 50%? Can I find the next brand, next grade in less than 5 years' time? I think the answer is yes, because we are making some progress in that direction. Again, using the same kind of approach, we do have the luxury of 30 years of data, both experimental and commercial data, which is a rich source of data-driven models. We have a fair bit of understanding of polymerization kinetics, particularly for polyethylene. So we combine data-driven models and detailed kinetic models to predict the performance. And that is now backfeeding into what kind of catalyst structures do we need to start the chemistry of polymerization with certain properties that we have in mind, whether it's recyclability, whether it's biodegradability, all the next generation of polymers that people need. Again, the same construct, different application, but systematically going through the same thought process. So hopefully, I have given you a flavor for the constructs that were laid out almost 3 decades ago are still being used systematically across a wide range of problems. The problems seem disconnected at the face of it, but the underlying principles remain the same. I want to close by just my own personal reflections with Professor Venkat. I was his PhD student from 98 to 2002, probably the best 4 years of my academic life. I do think the 4 things stand out for you, Professor. First is certainly you are insightful and visionary. You're way ahead of your times. A lot of the talks that I heard today reflect the same concept, and I think it's certainly true in molecular design. Second, I think your unique ability to integrate across various disciplines is something that stands out. Whether it's chemical engineering, chemistry, computer science, physics, even software engineering, things that are trendy now. We were talking about this almost 2 decades ago. You always encourage your students to expand our minds. I wanted to do a summer internship. We said, stay here in West Lafayette and study quantum mechanics or study complex adaptive systems. 20 years later, I see the value of that because I would not have expanded to learn these things hadn't you pushed me. And Marianthi spoke about genetic algorithms. I remember the first application of genetic algorithms was not in molecular design, but rather in heat exchanger design that Yannis had done. So again, connecting various different dots together. And finally, I think you're a very non-traditional, friendly, and a true mentor, which I personally appreciate. As the quote says, it's good to be clever, but it's better to be nice. I think you're both clever and nice. So I really appreciated my time with you as a student, and you made some great contributions to the field. Thank you.